So let's move to the next subtopic on diffusion through stagnant film. So we have two types of diffusion. First, the diffusion through stagnant film. So number 2 will be on the equimolar counter diffusion. Okay. So we will see both types of diffusion in both types of gas and also liquid. So for gas, we will derive the equation for equimolar counter diffusion, diffusion through stagnant film, and also we will see how the diffusion plus the convection happen in gas. So for liquid, we will have equation for equimolar counter diffusion and diffusion through stagnant film. Okay, so let's start with gases first. So let's see the equimolar counter diffusion in gas. So previously we already learned on the molar flux. Okay, so molar flux of component A, Z. Okay, so is equal to negative dAB dCA over dZ. Okay, so JAZ means molar flux. Flux is something that flows. So molar flux of A in Z distance. Z is the distance or the direction. So JAZ is the molar flux of A. Okay, so the Fick's law only focus on the single component, which is A. So how about when we have another component we call component B? So how can we calculate the molar flux? So if I can write here the molar flux of B, so I will replace A with the B. Okay, so it will become BZ equal to negative dBA dCB over dZ, isn't it? So if I have component B, I will use the same equation. So and I will replace A with the B. Okay, so to calculate the molar flux for B, component B or the species B. Okay, so here we make it simple. If we have dAB, how can we change to dBA? So if we have dAB and we want to calculate for dBA, okay, so you only need to change the sign only. Okay, so for example, dAB is equal to negative dBA. Okay, so you don't have to define, or you don't have to find the dBA. You just put negative on the value of dAB, so you will get negative dBA. Okay, so same thing like molar flux. So molar flux of A, species A, Z, is equal to negative of molar flux of B in Z distance. Okay, so if you have the value of molar flux for A, and the question wants you to calculate for species or for component B, so you just put negative to the value of A to get a molar flux for B. Okay, so very simple, I think. So you can see here, so JAZ is equal to negative dAB dCA over dZ. This is the original equation. So if you want to calculate for B, the flux for species B, so you just put negative to the JAZ, and you put negative and you will get the positive dBA dCB dZ. Okay, so this is, I think this is very straightforward. So this example 6.2-1 we will cover during the tutorial. Okay, let's move to the next types of diffusion. So diffusion together with convection. Okay, so when we consider Fick's law, so Fick's law, if you go back to the definition of the Fick's law means the individual movement, and Another thing is the movement of the individuals. Take into account that the fluid is not moving, the bulk fluid is not moving. For example, if I can draw here, so for example, if I have dye here, dye in the water, so this is the membrane, so I have dye here. Okay, the dye move from concentration of high to the concentration of to the low concentration region. Okay, so only dye move but not the fluid. Okay, the fluid will remain, or it will stay. So this is what we call fixed law. But in diffusion together with convection, so we consider how will the equation will be if the fluid is also moving. Okay, so we will see how the equation will be. So diffusion of flux dA occur because of the concentration gradient. Of course, I think this is you already understood this concept. So JA is equal to, this is flux of A. Flux of A is equal to velocity of A times with the concentration of A. So this is the diffusivity velocity, diffusion velocity of A times with the concentration of A. So we will get the flux of A. So this is the equation if the component A move due to the concentration gradient. So here is a term, is the same term, so but the unit is different. I think this is the last unit. Okay, JA is equal to VAD times with the CA. Okay, so now let us consider what will happen when the whole fluid is moving. Okay, let me draw. Okay, so for example, if I have water and I have dye here, so what happens if the dye move and the fluid is also moving? I mean the water is also moving. Okay, so both fluid and the component A is moving. So what will happen is the movement of both will result with this VA. A is the actual velocity of A. Okay, so VAD is the diffusion velocity of A, and VM is the diffusion the velocity of the bulk, I mean the fluid. Okay, so VAD is the diffusion of velocity of A relative to the moving fluid. So when both fluid and also the component A move, so it will result with a VA. Okay, so VA is the actual velocity of A. Okay, so VA is equal to VAD times with VM. Okay, so VA is equal to VAD times with VM. So VAD is again, VAD is diffusion of species A when the fluid is also moving. So VM is the velocity of the bulk. So the fluid is also moving. Okay, so the bulk is referring to the fluid. So we call it as VM. So VA is the actual velocity, is equal to VAD plus VM. So CA is, we expand the equation. So we will multiply each equation with CA. So each term with CA. So it will become CA VA, CA VAD, and plus CA VM. So CA VA also we can write in NA. So NA is the total flux of A. So CAVAD is actually the diffusion flux of A. CAVM is SCA. VM means the convective flux of A. So the final equation will be this one. NA is equal to GA plus CAVM. Okay, so CAVA will become NA, total flux, and CAVAD is equal to diffusion flux of A, and CAVM is convective flux of A. Okay, so convective means the situation where the component A diffuse or move to the right together with the moving fluid. So the fluid, for example, the water is also moving together. Okay, so the equation will be further expand. So for example, if I have total convective flux, okay, so CVM, so VM CVM is also called, we have NA and B